All right, welcome to our last Calc 2 lesson, everyone. So last time, what we were learning about was polar coordinates, which is an alternative way of representing points on the plane. And it also kind of provides us a means to draw curves that were difficult or maybe even inaccessible with Cartesian coordinates. So what we're going to do, so last time we were introduced to these, and now what we're going to do, kind of like what we did with parametric equations, is we're going to do a little run through calculus with these. Now, there is stuff to say about the derivatives of polar functions, but we're just going to focus on the integration side of things. So today's lesson is the area between polar curves. All right, so when we ever want to find the area underneath a curve, like back in calculus 1, between points A and B, then back then we would use the definite integral. So we would do the integral from A to B of f of x dx. Now let's suppose that now we have a polar curve. So let's say maybe our curve, I don't know, looks something like this maybe. So this is our angle A, and then this is our angle B right here. And we want to find the area within this curve right here. So we want to find all of this area. So you might expect like, okay, well then we'll just do the integral from A to B of our polar function. Because remember, last time we tried to view things in general as r equals f of theta. But it turns out that the area formula isn't just going to be the integral of this. It's going to be a little bit more complicated. So the area will be 1/2 the integral from angle A to angle B of f of theta squared d theta. Okay, now this seems a little bit strange. Where on earth does this come from? Why do we have to divide by 2? Why do we have to square things? By the way, forgetting this half is like one of the easiest mistakes you can make on this part of the material. So do not forget the 1/2 right here. All right, but where does this come from? I want to show you where this comes from real quick. So I'm going to make a little chart here. Shape, area, and angle. So let's say we have a full circle, right? And we have the area of the circle. So what's the area of a circle if its radius is r? It's going to be pi r squared. That's right. Now, what amount of angle do we have to get through the whole circle? It's going to be 2 pi. All right, so then let's say we have maybe the half circle. The area of this will obviously be 1/2 pi r squared, and the angle that we go through is pi right here. And then if we have a quarter circle, something like this, that'll be 1/4 pi r squared, and we go through an angle of pi over 2. So it seems like the relationship between how big of a chunk of the circle we have and the angle in its area is this. The area of a chunk of the circle is going to be 1/2 theta r squared. Because if we plug 2 pi in here, 2 and the half cancel, we just have pi r squared. We have pi over 2 here and so on. So the area of one chunk, or the fancy name is a sector of the circle, is 1/2 theta r squared. Now let's say we have something like this. Let's say we have some kind of polar curve spinning around like that. Here's our angle A. We go all the way to angle B here. So what we're doing is we're going to divide this up. Now, when we divided up area before in Calc 1, we divided it into rectangles, right? But what we're going to divide it into now are these very thin circle wedges. So we're approximating all of the twists and turns along this polar curve as just little tiny sectors of a circle. So since we're rotating through a very tiny angle right here, what are you going to think I'm going to call that angle? So what is this angle going to be? It's really tiny. It's going to be d theta. That's right. So what's the area of this sector of the circle? So the area of the tiny part will be 1/2 r squared d theta. All right, now that was one little tiny part. Now, what we do is we make those tinier and tinier, and we have more and more of them that fill up this region right here until we have infinitely many and they're infinitely thin, and that will give us an integral. So what we're going to do to get the real area is turn this into an integral. So we add all the tiny chunks together and then it forms an integral like this. And then lastly, since r is equal to f of theta right here, we just have f of theta squared. So where does this come from? It comes from the area of a sector of a circle. So that's why it has this kind of strange form right here. All right, that being said, let's go ahead and actually put this into practice. Let's go ahead and compute the area of something. Let's see here. So our first example is a curve that we saw last time. R equals cosine of theta. So remember what this curve looked like. It started out here. It came to the origin at pi over 2, and then from pi over 2 to pi, we ended up drawing the lower half. And then we ended up with this circle right here. All right, so since it took angles from 0 to pi to make this circle, that's what we're going to integrate. So we're going to integrate 1/2 the integral from 0 to pi, and then we also can't forget to square what our function is. So we're going to have cosine squared of theta. All right, now it's been a minute here. Do you guys remember how to integrate cosine squared? We do the half angle identity. That's right. So this is 1/4 the integral from 0 to pi of 1 plus cosine of 2 theta. All right, and then we do this integral, theta plus sine of 2 theta over 2 from 0 to pi. We plug pi in here. And then we plug pi in here. So we have sine of 2 pi is 0. And we have 0 here, and then sine of 0 is 0. So we end up with pi over 4 right here. How do we determine the bounds again? We determine the bounds by seeing which part of the circle is drawn at which angle. So for example, we start here at theta equals 0, and then we keep going through until we get to theta equals pi over 2. And then from pi over 2 to pi, we end up doing this part of the circle here. We get back here at theta equals pi. So my suggestion for any of these problems, whenever we're doing any kind of area, is to actually draw the picture. Because you might think, okay, well, maybe I'm just going to go from 0 to 2 pi because it's a cosine, but that would actually end up giving twice the area here. So you need to draw the picture to be aware of what angles you need to go through right here. Can I write the half angle identity? Yeah, sure. So the one for cosine squared is 1/2 times 1 plus cosine 2 theta. And the one for sine squared is the same, only we have a minus. All right, so that's a good review. We need to remember how to do the integrals of trig functions here. Now, before we move on to the next example, I want to show you guys another way of doing this. And I think a lot of people like doing these problems this way. So rather than find the area of the entire circle, what we could do is we could instead just find the area of, say, the upper half circle right here, and then multiply it by 2. Because the area up here is going to be the same thing as the area down there by symmetry. So another method is to use symmetry. So our area will be 2 times the area from 0 to pi over 2 of cosine squared of theta d theta. Now, another nice thing about using symmetry, or a nice thing about using symmetry, is that you often multiply by 2 or 4 or some multiple of 2, right? And that ends up canceling with your half there. So you don't need to worry about your half right here. Why is it not 2 pi? Because we were able to draw the whole circle along theta equals pi right here. So yeah, if you take a look at back at your notes from the last lecture, we were able to get around the whole circle only after pi radians right here with drawing the polar curve. But yeah, if we do this integral right here instead, then we will also end up getting pi over 4. So using symmetry can sometimes make things a little bit nicer right here. All right, so that was one type of polar curve we've drawn, but then there was another type that we drew last time. All right, so for our first practice problem, find the area enclosed by the curve r equals 2 sine of 2 theta right here. My hint for this is to use symmetry. Okay, so before we even start this was a curve that we drew last time. Does anyone remember what this looked like? What did this one look like? Yeah. Yeah, so this looked like a flower with 4 petals, right? And all of the petals were the same area. So it stands to reason that if you find the area of 1 petal, all you'd have to do is just multiply that by 4. So that's my hint for this. How much pi did it take to make 1 petal? Yeah, plug it in and see. So we started theta equals 0 here, and then we started going along this one. So plug in a few numbers to see how long it is. Are you going to have class technique to review for the final? Yeah, that's what we're going to be doing on Monday and Wednesday. Is going to be a practice final posted? Yeah, that'll be posted like sometime this weekend, probably. And yeah, no discussion. Yeah, no one's supposed to have a class on the reading days. When is the final? It's Monday the 26th. Oh, Wednesday's lecture be posted? Oh, sorry about that. I'll post that soon. And do we have discussion Tuesday? I don't think so. You could check the schedule though to be sure. I'm pretty sure we don't. All right, let's take a look at this. So what I'm going to do is I'm going to try to find the area of one of the petals, and it's going to be this one right here. And then I'm just going to multiply this by 4 to get the area of all 4 of these. So remember last time when we drew this, we went from 0 to pi over 4. That was the longest part of the petal. And then from pi over 4 to pi over 2, we went back down. So it seems like we're going to go from 0 to pi over 2 to get this petal. Now, someone's asked me this before, could we find the area of a half petal and multiply that by 8? And the answer is, yeah, you could do that if you want to. So it's kind of an interesting way of doing it, but I'm just going to do a full petal. All right, so there are 4 of them. And then the area formula is 4 times 1/2. The angles go from 0 to pi over 2. And then we can't forget to square this. So it's 4 sine squared of 2 theta d theta here. All right, let's see here. So 4 times 4 is 16 times 2 is 8. Or sorry, times 1/2. And then just like in the previous problem, we're going to use the half angle identity. That's going to be a big one for these area problems. So the 1/2 from the half angle identity will combine with this to form a 4. And then we have 0 to pi over 2, 1 minus cosine of 4 theta. And remember, it's a 4 theta because we always double whatever angle this is right here. All right. How do we pick the angle? You kind of have to draw out the curve as you're doing this. So when we start at theta equals 0, that's going to be right here. Then we go to theta equals pi over 4, that's out here. So our curve will go like that. And then from pi over 4 to pi over 2, we come back to the origin. So we're going to follow the curve along like this. Yeah, so it definitely helps to draw it out on your own to help you see which angles are going to go where. All right, so we get this part, and then now we just integrate here. So we have theta minus sine of 4 theta over 4 right here. 0 to pi over 2. All right, we plug in pi over 2 here. And then we plug pi over 2 into this, and we have sine of 2 pi, which is 0. We plug 0 into here, and then we plug 0 into here, and all that's 0. So we end up with 2 pi for our area right here. All right, but you also could have done this in other ways too. You could have just integrated from 0 to 2 pi and then not had the 4 right there. And there were other symmetries as well. But the point of this is that a lot of times when we have a single shape that's repeated, it may be worth our while to use symmetry. All right, so these are the areas enclosed within a single curve, but the title of the lesson was the area between polar curves. So sometimes we might want to have the area inside of one curve, but then outside of another one. Let's look at an example of that. All right. Find the area enclosed within r equals cosine of theta and r equals sine of theta right here. All right. So r equals cosine theta, we drew this one earlier. So r equals cosine theta starts here, then comes like this, and then from pi over 2 to pi, it forms this part. All right, and then sine of theta, we didn't draw this one specifically last time, but we discussed what it would look like. So cosine kind of goes in the x direction out 1. Sine will start at the origin and go out in the y direction out 1, and then come back. All right, so that was sine of theta. Now what we want to do is we want to find the area closed within both of these. So it's sort of like a Venn diagram here, meaning that we want to find the area right here. All right, now it's important for you guys to pay close attention to this. This is how we're going to think about all of these area problems. And any confusion that results can be solved by just thinking about it this way. The way we do area with polar coordinates is we pretend that we're standing at the origin with a laser pointer, and we're pointing it out to the curve that's our boundary. So what I mean by that is we want to get this, right? So what I'm going to do is I'm going to start at the origin, and I'm going to start shooting my laser pointer out along this curve, because this is the boundary of where I want to be. Now notice what curve I'm following when I do this. I'm following sine of theta. And I shoot my laser pointer all the way up till I get to here, which is the intersection of these. So we're following sine of theta from theta equals 0 to whatever angle this is. And the way we can get this angle is to set these equal to each other. So sine of theta equals cosine of theta. What angle is this going to be for the first quadrant? Pi over 4. So it seems like we're following along sine of theta from theta equals 0 to theta equals pi over 4. Now, if we were to continue to follow sine of theta, the problem would be that we would start overshooting our boundary here. We would start kind of going along this circle, but we don't really want to do that. We want to go along this right here. So what we do is once we get to pi over 4, we transfer over to following cosine. So we start shooting our laser pointer at the cosine curve and turning through angles all the way until we get back to the origin, which is at pi over 2 right here. So then we're following cosine from theta is pi over 4 to theta is pi over 2. So this is exactly how we're going to get the area of what we're doing right here. Will laser pointers be provided for the final? Yeah, sorry. Yeah, I'm not going to give you those. All right. So what we're going to do is we're going to find the area within sine from 0 to pi over 4. So that's 1/2 integral 0 to pi over 4. And then we square sine. And then we're going to do the same thing for cosine, but it's going to go from pi over 4 to pi over 2. Like that. All right. So then all we have to do is just do each of these right here. So we're going to use the half angle for both of them. So this will be 1/4, 0 to pi over 4, 1 minus cosine of 2 theta, and then 1/4 pi over 4 to pi over 2, 1 plus cosine of 2 theta right here. All right. So we have theta minus sine of 2 theta over 2. And then we have theta plus sine of 2 theta over 2. All right, let's plug in our numbers now. So I plug in pi over 4 and get pi over 4 right here. I plug pi over 4 into here. Sine of pi halves is 1. So I have minus 1/2. I plug 0 in for either of these and I get 0. And then for this next part, I have pi over 2. And then I add sine of 2 times pi over 2, which is actually 0. And then I subtract and I plug in pi over 4. And I subtract, I plug pi over 4 into here. Okay, and then this is pi over 4. Interestingly enough, notice that these actually gave us exactly the same result here. Can anyone explain why these numbers end up being exactly the same? Why is that? Does anyone see that? Yeah. Oh, so when we integrate, so the question was, shouldn't this be a plus right here? When we integrate cosine, we end up getting positive sign. So we keep the same thing. Yeah, don't worry. I mix that up all the time. It's easy to get the signs mixed up. All right. Yeah, so why do these end up being the same number? It's because that the area going for this first half of this little oval is the same as the area from the second half of the little oval. So another way we could have done this is we could have just doubled the first integral and then not done the second one. So this is an example where symmetry could have saved us some time here. But let's see, if we combine all of these together, we have 1/4 pi over 2 minus 1 So we have pi over 8 minus 1. All right. So yeah, I want to go over the bounds one more time because this is definitely a good example to do those. And remember, we're going to think about these bounds the same way for every problem. So my goal is to get the area of this chunk in here, right? So this curve is sine of theta, and this one is cosine theta. So remember, the way I imagine area with polar coordinates is I start at the origin and I start sweeping along different theta. So I start rotating. And as I rotate, my laser pointer kind of gets dragged along the wall. So I'm kind of gradually doing this. And as I'm getting bigger and bigger, I finally get to where these two curves intersect. So I start at theta equals 0, and then I go to where the two curves intersect. Now, where does that happen? Well, we set them equal to each other, and we see that happens at theta is pi over 4. So it seems like we follow along the sine part of this from 0 to pi over 4. Now, after that, we don't want to keep following sine, because if we shine our laser pointer at sine, we would accidentally go over the edge of where we want to go. So we're going to switch to following cosine at this point. So we're going to shoot to our cosine curve, starting at pi over 4. And then when we get to pi over 2, we hit the origin, which is the end of our petal here. So we're going to follow cosine from pi over 4 to pi over 2. So we just add those two areas together. Or we could have used symmetry. All right, let's do another example here. Let's do an example on something we haven't seen a picture of before. All right. So you could double the 0 to pi over 4 instead of going. Yeah, that's right, because the area of this first part, you can kind of see it's symmetric and it's the same as the second part of this. So we could have just doubled the first part right here because of symmetry. All right, this example is going to be a little bit strange, and this is kind of one of the strange aspects of polar coordinates. Find the area within the outer loop, but outside of the inner loop of the limmason r equals 2 cosine of theta minus 1. Now, a lot of these polar curves end up having kind of bizarre names, and this is one of them. This is limmason, and this is the little C thing. Sounds like S that appears in French here. So now let's think about what this means. So find the area within the outer loop, but outside of the inner loop. So that means that when we draw this, there's got to be two loops going on here somehow. So we got to keep that in mind when we're drawing this. And again, I always emphasize that you need to draw these here because of to get what your bounds are going to be. Let's make our little table here. Let's start at theta equals 0. If I plug in 0 for this, I have 2 times cosine of 0 is 2, and then minus 1 will be 1. So I'm going to be right there. Next, why don't we go by pi over 2 to save a little time here. So at pi over 2, cosine of pi over 2 is 0, right? Actually, wait a minute. I'll do something else first. So when this is 1/2, I have 2 times 1/2 is 1, right? And then 1 minus 1 will be 0. And that might be an interesting point. It's always an interesting point where r is equal to 0. So I want to see when that happens. Now, cosine of theta is equal to 1/2 when theta is pi over 3. So I'm actually going to do that. So cosine of pi over 3 is 1/2. And then times 2 is 1, minus 1 is 0. So it's going to start out at 1, but then when we get to pi over 3, which is maybe like right here, we're going to come back in to 0 right here. All right, then we can go to pi over 2. And cosine of pi over 2 is 0, and then minus 1 will be negative 1. So when we get to pi over 2, which would normally point this way, we're instead going to point the opposite way because we're negative. And we're going out the same distance that this is. Okay, this is kind of interesting. Let's see here. Why don't we go to maybe r is pi? So when we go to r is pi, we have 2 cosine of pi is -2 minus 1 is -3. So normally pi would point this way, right? But since we're negative, we're going to go the other way. And 3, that's going to be all the way out here, like this. So this is at theta equals pi, right there. Let's do 3 pi over 2. At 3 pi over 2, cosine is 0, so we come back to -1. So we're going to come back. 3 pi over 2 is normally this way, but since we're negative, it'll be here. Like this. And then we're going to make a little stop here. We'd normally go by pi over 2s, but I'm going to stop at 5 pi over 3. That's going to be significant because once again, cosine will be 1/2, and 2 times 1/2 is 1, minus 1 is 0. So when we get to 5 pi over 3, we're going to hit 0. And then when we get to 2 pi, we have 2 minus 1 is 1. And then we end up back where we started here. So a limacon is this shape that ends up having this kind of big outer loop right here, but then it has a small inner loop right here. That's what they're talking about. This whole big thing is the outer loop, and then we have this inner loop right here. So kind of like parametric equations where they could self-intersect, these can self-intersect as well. Now remember what we were tasked to do here. We're supposed to find the area within the outer loop, but outside of the inner loop. So we want to find the area within this whole thing except for this right here. All right, so let's see how we would do that. All right, let's see. So if we start at theta equals 0, we're going to be going out here, right? And then as we rotate to theta is pi over 3, we're going to get this half of the little loop. So what my goal here is I'm going to do the area of the whole thing minus the area of the inner loop. Because I can get the area of the whole thing, so like if I shade all of this in and then just take away the area of the inner loop, and that would give me what I want. So I need to find out what the area of the whole thing is. I need an integral for that. And then I have the area of my inner loop right here. I need to take that away and find an integral for this. All right, so the area of the inner loop. So we drew this from 0 to pi over 3, right? And that gave us half of that area. So why don't we just double that? So the area of the inner loop here is 2 times 1/2, the integral from 0 to pi over 3, and then we double this, or square it, excuse me. All right, so this is going to be our area of our inner loop. Now let's think about the area of the whole thing. So when we hit pi over 3, we start going this way, right? Remember when we drew the curve, we started drawing this part next. And then we keep going this way. Now remember, we're shooting a laser pointer all the way to where our curve is, right? And once we get past pi over 2, our curve starts being here. But look at what's happening. In order for our laser pointer to touch the curve, we're going through and including the area of our inner loop. That's what we're measuring all the way from here to here. So the integral from pi over 3, so pi over 3 starts here and goes this way, and then all the way to pi, which ends here, this is not only going to get half of the area of the big loop, it's going to get half of the area of the whole thing, including this. So all I need to do is double what I just got here, and that gives me the area of everything within all of this right here. So I'm going to do 2 times 1/2, integral from pi thirds to pi, and then I have 2 cosine of theta minus 1 squared. All right, and there we go. So if I double this, I get the area of everything, but then I want to take away the area of the inner loop right here, which is this right here. So in this case, I'm going to do two different integrals, which actually have the same integrand right here, but they're just going to be integrated over different bounds right here. All right, so that's how we set that up. And remember that laser pointer philosophy is going to be our guiding philosophy for setting up these integrals. Now, the nice thing about multiplying by 2 is that it cancels with 1/2. So we're just going to be left to integrate these. So we have pi over 3 to pi. And then we have 4 cosine squared of theta minus 4 cosine of theta plus 1. And oops, we're not adding, we're subtracting. And then we have this right here. All right. So let's see here. Let's do this integral here. Well, before I do that, I use the half angle on this. And this is 2 plus 2 cosine of 2 theta. All right. Now that I've done the half angle here, I integrate. And I have 2 theta plus sine of 2 theta minus 4 sine of theta plus another theta. And because this is the same function as this, I end up getting the same thing over here automatically. And the theta and 2 theta form a 3 theta. All right. You mean the pi over 3 to pi? Oh, so I used the half angle identity here. So I got a half from that, changing this to be a 2. And then it's 1 plus cosine of 2 theta. So I just distributed the 2 there. Why do we start at pi over 3 for the first integral? Because pi over 3 is where we start to go over this little bit right here. And then we rotate around and start getting all of that. So pi over 3 is where we exit the little loop. All right, and then we'll plug all of this in right here. And I'm just going to try to save some time.
Why is the second one 3 theta versus 2 theta?
It's theta plus 2 theta right here. So I just combine it to 3 theta in the other one.
Oh, okay, I see it.
I'm just going to save some time with this one here because I want to make sure we have time to go over our last example here. So if we plug in all of these numbers and everything, we end up getting pi plus 3 root 3 right here. That's what we get when we plug in all of the numbers right here. All right, so there we go. So the moral of the story is that when we're shooting at the laser pointer, we even cross over other curves on our way to the one that we're following. So that's kind of the important lesson here. All right, now let's do practice 2. Now I'm going to help you guys out with practice 2. I think I accidentally made this a bit too hard. So we're going to find the area enclosed within r equals cosine of theta minus 2 and r equals sine of theta minus 2 right here. All right, to help you guys out, I drew a picture of this. So if you guys ever want to plot polar curves, you probably use this for other things, but Desmos is actually a really good way to plot polar curves. So let me share. So I'll give people like 30 seconds to write this down. So find the area enclosed with these two, and then I'm going to show you guys a picture. So write this down, and then we'll switch over. Oops. Okay, can everyone see the Desmos plot here? All right. So our goal is to find the area within these two curves right here. Is it a -2? Oh yeah, I was playing around with this. It ends up being the same thing, but yes, we have cosine theta -2, and then sine of theta -2. There we go. All right, so the blue curve is going to be sine, and then the red curve is going to be cosine. And these sort of end up making these almost circles. They're circles, but then they're just a little bit squished on one side. Like this blue circle is kind of squished on the bottom side here, and then this red circle is squished on the left side here. Yeah, it is. Yeah, a flat tire is a good way of thinking of it. Yeah, that's what's going on. Now, what we want to do is we want to find the area kind of in the center of the Venn diagram of these two right here. That's what we want to do here. Now, usually the hard part about these is setting up the bounds, right? So we need to figure out what our bounds are going to be. So let's start tracing through these curves here. So why don't we start with cosine -2? So if I plug in theta equals 0 for the cosine, which is the red one, cosine of 0 is 1, right? And then -2 will be -1. So at theta equals 0, r will be -1. So I start at 0, but then since I'm at -1, I go backwards. And so here's my curve right here. So I'm right here. Can you guys see my mouse over Zoom? You can see my mouse? Okay, good. All right, so yeah, so we're going to start right here. And then as we rotate through, notice the cosine's always less than 1, right? So this will always be a negative number. So say when we get to pi over 4, which would be right here, rather than going out this way, we're instead going to be going this way because we're always having a negative r. So the way we're tracing out the circle is we start at theta equals 0. They intersect at theta is pi over 4. Here we're at theta is pi over 2, 3 pi over 4, pi. And then we have what, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. So unlike a lot of the other circles we're doing, we actually go through this one in the opposite order. And that's because our r is negative the whole time. Now, the important points are where this intersects with the sine theta curve. So this seems to intersect there at pi over 4. So the way, all right, so enough about explaining what these circles are. So the way we're going to do this is I'm going to try to get the area on the lower half, or kind of the lower and to the right half of this intersection right here. So I'm going to start at pi over 4, and then I'm going to follow the blue curve around. So I'm going to kind of shoot lines out from the center to the blue curve. Can you use symmetry here? That's exactly what we're going to do. So we keep shooting out lines to the blue curve, and then we get to here. Now notice that once we went around the blue curve, we got half of the area that was in between these. So what our integral is going to be is it's going to be the integral from pi over 4 to 3 pi over 4, that's where they intersect on this side, of sine of theta -2 squared. That's what we're going to end up integrating here. So again, I'll explain this one more time so we get what's going on. So we start here at pi over 4 where they intersect, and then I'm following along the blue curve because that's the edge of this Venn diagram thing that I want. So I'm shooting my laser pointer out to my blue curve right here until I get to this point right here where they intersect. And then I stop because I've gotten half of this Venn diagram when I get there. So overall, my integral is going to be from pi over 4, sorry, not 3 pi over 4, 5. My integral is going to be from pi over 4 to 5 pi over 4 of the sine curve squared. All right, so let's flip back to the paper and take a look at that. Okay, so our area for this will be 2 times 1/2 the integral from pi over 4 to 5 pi over 4. And then remember, we were following the sine curve. So this is going to end up being our area right here. And again, the way we figured out this area is we looked at a picture of what was going on here. We could have graphed this ourselves, but I wanted to make sure we had enough time here. So I graphed it on the computer. But we looked at the graph and then we saw which angles we were touching the area that we wanted to touch here. All right, and then let's see, we have enough time to actually do this. Now we can get started. So the 2 and the 1/2 cancel. And if I were to FOIL this, I would have sines, oops, getting a little low. I have sine squared of theta minus 4 sine of theta plus 4 d theta right here. All right, so let's see here. Sine squared, we can use the half angle identity on that. So we have 1/2 minus cosine of 2 theta over 2 minus 4 sine of theta plus 4. And then we integrate this. By the way, 4 and 1/2, I'm going to combine these together. That's going to make 9/2. So I have 9/2 theta minus sine of 2 theta over 4, because I divide by a 2. And then I have plus 4 cosine of theta. From pi over 4 to 5 pi over 4. Is it common to use the half angle identity when we're finding the area of these? Yeah, the half angle identity is really common. I think we've used it in every problem today, if I'm not mistaken. Yeah, so I would definitely brush up on that. All right, and then we plug in 5 pi over 4 and pi over 4 here. And let's see here. Again, I'm kind of just going to speed through this part right here because it's just plugging in numbers into the trig function right here. After some work, after plugging in these numbers right here, seeing what's going on, we end up with 9 pi over 2 minus 4 root 2 here. All right, now one final thing I want to say about these areas is the area of all of these will end up being positive if we do this correctly. So when you're checking your answer, well, like when you're checking your work here, one way to see if you've gone wrong is that if you end up getting a negative answer right here. So for example, if maybe this was the other way around, I have 4 root 2 minus 9 pi over 2. I kind of feel like 9 pi over 2 is a bigger number than 4 root 2, because this is like 4.5 times pi. And both of these numbers are bigger than these ones. So this one should definitely be in front here. So if we ended up with that in the front and the 9 pi over 2 being subtracted, we know we did something wrong at some point. Maybe we dropped a sign or something like that. So remember, your answer should always be positive for these. All right, so always be positive. Yep, that's what I said. All right, so let's see here. I think that's about it. Also, I saw a question earlier asking, will we have enough time to draw the graphs? Yeah, it'll either be a relatively simple graph, like it'll either be like the petal, like the flower with like 4 petals or something, or if it's a complicated thing, we'll just give you the graph right here. All right, so then that's it for all the lessons. So we're finished learning new material for Calculus 2. So like I said, next week we will be reviewing for the final, which is on Monday, April 26th. All right, so I will see you guys on Monday.